today we're going to continue looking at this idea of calculating distances to stars from the Earth. As mentioned before, the distances in this topic are ridiculous, but based on the Earth we can still get a huge amount of information about what we can see in the sky. So parallax was the first step. How can we calculate how far away stars are? Parallax has limits because of our atmosphere, so we need other techniques in order to find distances to things that are further away. Well, we're going to use luminosity and apparent brightness to find distance. We're going to look at surface temperature. How can we find the temperature of a star, and why is that useful? And we're also going to see how, from the Earth, looking at the stars and their colours, etc., particularly their spectrum, can we actually learn anything about what the star is made of? So those are three things. We're going to be looking at distance, we're going to be looking at luminosity, brightness and distance specifically. We're going to be looking at the spectrum and how that can help us to find distance. And then we're going to be looking at the spectrum and how that can help us to look at chemical composition. Now, if we review first the inverse square relationship, this came up in topic 4, and it relates the intensity, the brightness of a star, to how far away you are from it. Now, as you should remember, it follows a 1 over d squared relationship. So if you are a certain distance d from a star, the intensity is I. If you double that distance, then the intensity would be 1 over d squared. So it will be 1 over 4 that distance, right? And then if you make the distance 3 times bigger, it would be 1 over 9. Now, intensity is, we're going to use a slightly different quantity to make it specific to astrophysics, right? So in astrophysics, intensity is referred to as apparent brightness, but pretty much it's the same thing. If you are sitting on the Earth looking at a star with a telescope, you would measure its intensity, the power over unit area, and call it apparent brightness, the same thing. The units are watts per square meter. The luminosity of a star, the brightness of that star, okay, is equates to the power, right? So that's actually what's happening in the star. How much energy per second is the star itself giving off? That we would call the power. The power, the luminosity per square meter, would then be the apparent brightness. Now, how do we calculate the apparent brightness? Well, if you imagine all that power concentrated in this point and then spreading out, so that energy that's given off per second, as it spreads out in a sphere, so it's now, that same power is now spread out over that entire surface area there. Okay, so what we're looking at is the power divided by that surface area. It's a sphere, so you need to use the surface area 4 pi d squared. That apparent brightness, B, is equal to the luminosity divided by 4 pi d squared. And that gives you the apparent brightness. So this you measure from the Earth. This, I'll tell you how we work that out in a moment, but then you can work out that distance using the relationship. Have a go with this question. If you have a star of luminosity 6.3 times 10 to the 27 watts, which is at 7.9 times 10 to the 13 kilometers from the Earth. Remember to convert your kilometers. Calculate the apparent brightness. How bright would it look from the Earth? Stop the video now, and when you've done it, check your answer. Hopefully you got a value of 8 times 10 to the minus 8. Simple. Okay, now we're going to look at stars and temperatures. And the first thing we kind of have to think about is our perception of the night sky is not exactly how it should be. We are subject to a considerable amount of light pollution, unless you're lucky enough to live in monasterios far away from anything else. You don't normally, living in a city or an urban area, see many stars up in the sky. And if you do, most of them seem quite similar. Once we start looking in very isolated areas, no light pollution, with the correct equipment, you start to see that the night sky looks very, very busy, actually. And not only that, there is a massive diverse variety of colour in the stars. They have bluish, reddish, yellowish hues. And that's the first thing you kind of have to get your head round. There are stars which definitely have a bluish tinge to them. So you've got here Spica, Virgo, and then you've got our own sun, which definitely is an yellowy, is definitely peaking in that yellow colour. And then you have other ones which are Antares. Now, these colours are indicative of two different things. One of them is the rate that they're moving, but secondly, we're not going to think about that till next week. What we're going to look at now is the fact that those colours are indicative of their surface temperature. Now, hopefully that sounds familiar to you. The idea that a colour might be representative of the temperature. And that's right. We looked at this in topic 8, black body radiation. The colour of a hot body or a hot object is directly proportional to its temperature, right? So for every temperature, an object will always peak. It will give off a whole range of wavelengths. So if we look at this star here, which has a temperature of 2,500 Kelvin, it's giving off all of these wavelengths, right? It's giving off the 1,000, 3,500, 6,000, 8,500, 11,000. It's giving all of these. But the radiation it's giving most of is in this range here. It's actually a little bit more, so it's actually peaking in the infrared. But the colour which is most prevalent and most intense is red. And that's why this star, using the correct equipment, will slightly peak and will give you a reddish hue, right? It would look like a reddish star. And then similarly, a star which is blue is because its peak is either in the blue spectrum or in the ultraviolet spectrum. And so therefore it's giving off maximum intensity in that blue wavelength or blue and violet wavelength. So the temperature is going to be much greater. Now, how do we work that out? If only there was a relationship that would link temperature to wavelength. Oh yes, there is. Yes, Wade's displacement law, which we did in topic 8. So how do we calculate that temperature? Well, from Wade's displacement law, the maximum wavelength, the wavelength of that peak, times the surface temperature of the star will be equal to 2.9 times 10 to the minus 3 meter kelvins. So we can use this relationship to work out the surface temperature from what we see on Earth, the wavelength. The next step, of course, is what do we do with that temperature? Well, we're looking for luminosity, right? We want to use that apparent brightness equation to find distance. So we can find luminosity from power equals emissivity times the Stefan-Boltzmann constant times area times temperature. Okay, for a star, we assume that the emissivity is 1. And the Stefan-Boltzmann constant is the same as in topic 8. Have a quick practice of that equation just to remind you. If the luminosity is the Stefan-Boltzmann constant times area times t to the 4, what is the luminosity of a star of radius 2.7 times 10 to the 6 kilometers? Remember to convert that. And a surface temperature of 7,120 Kelvin. Now remember the Stefan-Boltzmann constant, 5.67 times 10 to the 8, and And to quickly remind you, the surface area would be 4 pi r squared for any sphere. Okay, that's a very important relationship for this topic. 4 pi r squared. Okay, so have a go, stop the video and see if you get the right answer. So the luminosity of a star would then be 1.33 times 10 to the 28 watts. So just to end on the idea of emission of radiation, we're going to look at the last section, which is how do we investigate what a star is made from? I mean, how from the Earth, considering the distances involved, can we investigate and discover what a star is actually made from? Now, the physics of it is actually very, very straightforward. It's to do with absorption spectra. And just to review, if you remember, any hot object will give you a continuous spectrum. This goes back to the peak. Any hot object will give a whole range of wavelengths, right? And that's called a visible spectrum. Now, if you have a hot gas or an object which is absorbing energy, what we're interested in here is the continuous spectrum with dark lines. That hot gas will absorb very, very specific wavelengths in that continuous spectrum. What wavelengths are those? Those happen to correlate perfectly with the energy levels of specific elements, right? So the electrons in the gas will absorb wavelengths equivalent to the photons of energy that it needs to jump and change level. So what we're doing on Earth is we're looking at the spectra given by stars and looking at the absorption wavelengths in order to identify the elements involved, because of course each element has a very specific pattern of absorption spectra. So by looking at these, we can see what the stars are made of. And generally, what we're finding is that most stars have a considerable amount of hydrogen, helium, and a possibility, a small, very, very small amount of other elements. But we continuously see the hydrogen and the helium spectra. So it's always the same pattern of absorption, right? So we use absorption spectra, possibly even emission, but we'll go into that next in the next topic if we have time. Absorption and emission spectra to look at the chemical composition of stars. And that's it. That's all you need to learn for today.